next interface that we will look into is for the analog to digital converters or ADCs. As you know that real world is analog in nature. So, though we try to get the signal values inside the microprocessor or microcontroller in digital terms, and we do the processing in digital terms. So, the real world is analog. So, the signals that you get from the environment, so they are analog in nature. So, to get the values from the nature, so we need some facility by which we can read those values. For example, if you are say reading the temperature of a room, so that is even if it is converted into some voltage, so what you get is a continuous range of voltages. Or if you are monitoring the flow of a say speed of a train or say speed of a belt, conveyor belt, so that is also a continuous quantity that you are getting. So, but unfortunately the microprocessors and microcontrollers, they are digital in nature and they cannot process this analog data directly. So, what is required is that we should convert this analog data into some digital values. Okay. So, these are done by the chips which are known as analog to digital converters or ADCs. They are used for data acquisition, that is for collecting data from the environment, physical quantity converted to electrical signal using transducers. So, transducer means this is some device by which you can convert physical data into say into a electrical signal. For example, a very simple transducer are the light dependent resistors or LDRs, light dependent resistor. So, if we want to detect the light, okay, if you want to detect the light, so it is a structure like this. So, this is simply a resistor, but this value of this resistance will depend on the light that is falling onto it. So, a typical design may be that when there is no light falling, so this resistance is say infinity or very high, and when some lights are falling onto it, the resistance will decrease. So, you can have a very simple design like this. So, you can have a very simple design like this. So, you put a resistance, a current limiting resistance, and this is the LDR. Okay, this is the LDR. So, this is connected to some supply voltage VCC, this is grounded, and from this point I am getting the value. Okay. Then what will happen is that when this when light is not there, then resistance is very high. So, you will get here voltage almost equal to VCC, there will be very little current flowing through this device. So, you will get the voltage around VCC, but when some light is falling onto it, then its resistance will decrease, and if depending upon the amount of light that you have, so this resistance will be varying. So, if I go for the maximum possibility, then this resistance will be close to 0. As a result, this point will be almost grounded. So, you will get almost a 0 volt there. So, this is the this is the electrical signal converted form of the light that is falling onto the system. Okay. So, that way there are many such transducers, like we have got these pressure transducers, then different type of sensors, gas sensors and other sensors that we have. So, they all come under the heading called transducers. Now, these transducers may be linear or the transducers may be non-linear. So, linear transducer means that with the amount of excitation that you have, the corresponding electrical signal that is produced is proportional to that. So, it is ideal that I have a behavior like this. Okay. So, if this side is the excitation, and we have got say the electrical voltage, the electrical signal there, maybe voltage, maybe current. Okay. So, whatever it is. So, I would ideally like to have a straight line like this. It may not be at 45 degree, but it is more or less a straight line. So, I would like to have a behavior like this, but this seldom happens, and normally we get different types of behavior. Maybe it will go like this, it will have a behavior like this. So, what is required is that we have to identify the range, and depending upon the range we have to do some sort of piecewise linearization or something like that. But ultimately, so this say what I mean is that this transducer alone is not sufficient for this purpose. Okay. This transducer output, it goes through some circuitry which we call in general the linearization circuitry, and from this linearization circuitry it goes to the converter. So, this is the data converter that we will be talking about in our course. So, that is the analog. So, up to this much I have got the analog signals. So, as this is the environmental excitation that we are getting to the transducer. So, it is producing some analog values. That analog value is linearized and then we get some linearized analog values here, but this is also analog. So, ultimately it goes to the data converter and here what you get are the digital quantities. They are the digital quantities. So, these digital quantities can be processed by microprocessors and microcontrollers. So, our part of discussion is around this. So, we do not talk about this linearization circuitry. So, that you can find in some analog electronics course. So, we are not going to that. So, we assume that these linearized electrical signal values are available and then we are going to convert it from analog quantity to digital quantity. So, the device that is mostly used for this purpose is known as the analog to digital converter or ADC. So, an ADC can have n bit resolution in 1 upon 2 power n is the bit step size. So, like if I say that this transducer is producing some voltage, now what is the difference in voltage that it can convert it into digital? Like see if I have got if there is a if there is some electrical signal of say 2 volt, accordingly suppose this device that I have, this ADC, it produces some output, say it produces a 4 bit output, so 0 1 0 0. Then the next closest output that it can produce is 0 1 0 1, the single LSB change, fine. Now, single LSB change, now for what change in this voltage it can produce this single LSB change. Okay. So, if the next voltage is 2.2 volts, such that for 2 volt output is this one, for 2.2 volt output is this one, then I can say that it has got a resolution of 0.2 volt. So, it is for it can sense the change of 0.2 volt and convert it into a different digital value, the next digital value. Okay. So, in general I can say that if the total range of voltage that you have here is say V and the total number of outputs that, so if this ADC is producing an n bit output, then you can understand that it can produce 2 power n different values. So, those 2 power n different values will correspond to this 2 power n different voltage levels. So, I can say this V upon 2 power n. So, this may be taken as the resolution of the this ADC, because ideally, so this entire range is uniformly divided. So, it is not that say V equal to say 5 volt. So, it is not that for 0 to 1 volt it produces values which are close to each other, from 4 to 5 volt it produces values which are far away from each other. So, the corresponding change in the input voltage that is required to change the LSB is different over different range of voltage value. So, if that is happening, so we are not really happy with that situation, because then this conversion does not have much belief in that. So, ideally I would like to have a system where this range is uniform. Okay. So, each of them are converted into proper values within the range. So, it has got an n bit resolution, and then this n bit resolution is having this n bit resolution has 1 upon 2 power n as the step size, and conversion time, there is a quantity called conversion time. So, which is the time needed for the conversion. So, it is not that the analog value changes continually and still this digital ADC will be following that value, the analog value at the same rate. That may not happen. So, normally these devices, they take some time to for doing this conversion, and there are different types of ADCs. Okay. So, we have got simple successive approximation type, where it just goes on changing the bits one by one. First it changes the LSB, then compares the resulting value with the corresponding analog value, and if it is not sufficient, then it will be changing again the next bit. So, it will do like that. So, we have got successive approximation type up to say flash type, where this conversion is parallelly done. So, all the bits are checked parallelly for the possible values. Okay. So, that way we have got different classes of ADCs. So, the conversion time will be different for each of them. So, this is one example ADC, ADC 0804. So, it has got a number of pins there. So, we will see about this pin the name of these pins and their meaning in successive slides. So, this has got 8-bit resolution. So, that n equal to 8 bit. So, if you look into this diagram, you see that it has got dB 1 to dB 6 and this dB 0 to dB 6 and dB 7. Okay. So, this is the ADC output. So, this is producing an 8-bit output. So, that n equal to 8. Okay. So, total resolution is that is why it is said an 8-bit resolution. So, we have got this 8-bit resolution and differential analog input voltage inputs. So, if we so, we have got this analog input voltage in V in plus and V in minus. Okay. So, this differential voltage, so this is useful because it will have less error, okay, in the input that we are getting. So, if you are giving a single rail input only V in and that is with respect to ground. So, that way, so possibility of error will be more. Like if there is some error which is some error which affects both of them equally, then since these pins are very closely located. So, if there is an electromagnetic interference or something like that which affects pin number 6, then it is very much likely that it will also affect pin number 7. So, the input is taken as 6 minus 7. So, as a result those noises they will get cancelled out. So, common mode noise they will go. So, that is the purpose of having this differential input. Then 0 to 5 input volt range. So, as I was telling that the range of inputs that it can convert from analog to digital, the analog signal value can be in the range of 0 to 5 volt. Okay. There is no zero adjustment. Some of the ADCs that you have, so there is a pin by which you can do a zero adjustment, means if you give a 0 volt at the input, then what is the corresponding output. So, we expect that the output should also be 0. So, 0 or for that matter the minimum possible range value that you have. So, if you give that, it is expected that the output should be 0. So, it should be, if it does not happen, then there is a problem. So, in this case this 0 adjustment facility is not there. There is a built-in clock generator, because when this ADC is operating, so it requires a clock signal. So, for some of the ADCs there is a built-in clock circuitry, so which can feed its clock directly, or you can have some in some ADCs. So, you have to connect externally some clock generator, maybe coming from the microcontroller or maybe coming from some circuitry, maybe say 555 timer based circuitry, from which the clock is generated and fed to it. Then the voltage at Vref by 2 can be externally adjusted to convert smaller input voltage spans to full 8-bit resolution. So, this is the pin Vref by 2. So, Vref by 2. So, if your input voltage range is not in the range of 0 to 5 volt or something less than that. So, you can connect some value here by which you can say that okay, my input is not in that range. So, it will be less than that. So, that way it can be said. So, important chips pins that we have in this case, first one is the CS, which is the chip select. So, chip select is an active low pin and is used to activate the ADC. So, just like any other device that we connect with microcontroller, so there has to be a chip select line, because the data bus line that you have from this microcontroller from the ADC will also be driving the data bus of this microcontroller, to which other devices are also connected. So, this chip select line should be low for the chip to be for the ADC to get selected. Then there is a read or RD pin. So, this is an input pin and is active low. So, ADC will store the result in an internal register after conversion of analog data, and this pin will help to get the data out of ADC. So, you apply an analog voltage and tell the ADC to convert it. So, it will convert the value, but it will not put it onto the data bus immediately. So, it will hold the value in some internal register. So, to read the value of the value from that register onto the data bus, so what is required is you should make this read bar pin low. so that you get the value in that register onto the data bus. So, when CS equal to 0 or CS bar is activated, a high to low pulse will be given to the read pin, and then the digital output will come onto the D0 to D7. So, this is read line. So, this requires a high to low pulse, that is a low falling edge triggered operation. Then there is another pin which is write WR. So, this is also an input pin and active low, and this initiates the conversion process. So, in some of the processor, some of the ADCs, so there is another pin which is known as start conversion or SC, start conversion. So, in this particular ADC, so we do not have any separate start conversion line. So, we have got this write line. So, if a high to low pulse is given onto this when we make this low to high transition on this write pin, then this ADC will start converting, because once the data has been put onto the once the analog signal has come. So, this microcontroller should tell the ADC to start doing the conversion, otherwise there is no point converting all the values that are coming onto the analog line. So, analog line will continually change its value because it is coming from the environment. So, it can continually change its value. So, the microcontroller may not be interested in getting all those converted values. So, whenever it feels that I should get the corresponding digital output, so it should set this start conversion signal or the write signal and give a low to high transition on that with CS equal to 0. Okay. Then the ADC conversion process will start. Then we have got clock in. So, if you have got an external clock source, then you can connect this clock line there. So, this will be acting as the external clock source. As I said that the 0804 has got internal clock source as well. So, if you think that I will be working with an external clock, so you can do that. Then there is an INTR pin, so which is an output pin and active low. When the conversion is over, this pin will go low. So, when this you think about the situation like you have connected one ADC with a microcontroller, and you have microcontroller has given this CS bar and write bar CS bar signal and given a low to high transition on write, so that it starts converting. Now, depending upon the type of ADC, so it will take some amount of time to do the conversion. So, what does the microcontroller do in that period of time? So, one possibility is that the microcontroller will be continually checking whether the conversion is over or not, and other possibility is that microcontroller will go to some other job, it will do some other job, and when the ADC is done, so it will give an INTR signal to the microcontroller, the interrupt signal to the microcontroller telling that the conversion is over. Accordingly, so it may be this particular line may be connected to say for 8051, so it may be connected to INT0 or INT1 pin, and accordingly it will be jumping over to the corresponding ISR. In that ISR, so we can activate this read bar line, and accordingly we can get the content of this converted value. So, this is other pins. So, V in plus and V in minus. So, they are the analog input. So, this differential input as I said. So, so maybe you just connect if you do in the simplistic case, the V in minus is connected to ground and the V in plus is the signal line. Then we have got analog ground, so which is connected to ground, and there is a Vref2 is the reference voltage. So, used to set the reference voltage. So, default reference voltage is 5 volt when not connected. If you keep this Vref by 2 pin open, then the reference voltage will be 5 volt, and when if it is connected, then the reference voltage will become 2.5 volt, and accordingly step size is can be reduced by using this pin. So, if say if you are instead of converting 0 to 5 volt, if you are converting in the range, so 0 to 2.5 volt, then what will happen is the same 8 bit ADC. So, you are getting same 256 levels of inputs converted into digital values. So, if the range is less, that means your resolution will be higher, because now you can have less the difference in the LSB in the analog voltage that will produce change in the LSB. So, we have got this VREF by 2 pin. Then there is a digital ground pin, so DGND. So, that is also connected to ground, and this D0 to D7, these are the output data bits. Then we have got clock R, so for resetting the clock, and there is a VCC power supply. So, it is a power supply for the ADC. So, these are the important pins that we have for this ADC. So, this is a schematic diagram in which we have connected one 8051 chip with this ADC 0804. Okay. So, as you can, so in this case this port 1 has been used for getting the data. So, this port 1 is connected to this this LSB is D0 is connected to P 1.0 and this D7 is connected to 1.7. Port 3 has been used for driving the other signals like the chip select, read, write and interrupt. So, these are the signals given for this operation, and other values like this V in is coming from say the V in is connected this is input to the microcontroller by means of this it is connected to this ADC by means of this 10 kilo pot, so that we can change this pot position to give different analog input values to the ADC, and this ADC will convert the value accordingly. Then this V in minus and this analog input ground, so analog ground, so they are shorted, and we have to connect a resistance and a capacitor here. So, this is required for that clock generation circuitry. So, internally it will generate clock. So, this circuitry will do that. So, the VREF by 2 is not connected and supply voltage is 5 volt. So, that is the side we have got for this 0804 ADC. On this 8051 side, I have already said that port 1 is used for getting the data bit lines, port 3 is used for giving the control signals, and suppose in port 0 we have connected a number of LEDs. Okay. The number of LEDs are connected. So, whatever digital value will be obtained here will be put onto port 0, so that on port 0 you can see the corresponding bit pattern glowing. Okay. So, that is done here. So, this is the interfacing circuitry. Now, the structure, the program structure will be something like this. So, origin 00 hex means that the program will be compiled from location 00 hex. So, first of all this P1 has to be put in the input mode. Okay. So, this if you look into this port, P1 is connected as input from D0 to D7. So, P1 has to be converted, P1 has to be configured as input port. So, this is done here. Then we select this chip select line and make it equal to 0. So, this clear P 3.7. So, this will put this CS line equal to 0. Then set bit P 3.6. So, this will make this read line high, and clear P 3.5, it will make the write line low. Then we put set B 3.5. So, this will be giving a high pulse to the right for start conversion. So, this read line should not be set now, because a high to low transition on the read line will be needed for reading the content of the ADC, the converted value, but for starting the conversion, so we need to put a low to high pulse on this right bar on the right line. Okay. So, that is done here by clearing this P 3.5 and then setting P 3.5. Then we wait till the INTR becomes equal to 0. Okay. So, this is JB jump on bit P 3.4 wait. So, if you look into this diagram, P 3.4 is connected to the INTR line from ADC. So, it can be programmed as interrupt, but in this sample program, so we have not done that. So, we are just waiting on a busy loop till INTR becomes equal to 0. So, once INTR becomes 0, so it will come to the next statement, it will clear P 3.7. So, it is chip select is, so this is done again. So, we have already done we have already cleared P 3.7. So, this may be an extra caution. Okay. So, we are clearing CS bit by clear P 3.7, then we clear P 3.6. So, that gives a low to high to low pulse on the read line. So, read line was previously set to here it was set to high by set B 3.6. So, it was set to high. but here it is cleared. So, we get a high to low pulse on the read bar line. After that, the data is available on the data bus on the. So, it is the D0 to D7 line of the ADC, it is containing the converted value. So, that I have to read it onto the port P1 on the port P1. So, that is done here, move A comma P1. So, from the digital data will come to the accumulator. Now, we want to display it. Now, for the display part, you see the way these LEDs are connected. So, if this P 1.0 was say equal to 1, so to glow this LED I have to put a 0 here. Similarly, if this bit is 0, I do not want to glow this LED. So, accordingly I should put a value of 1 at this point. So, this way you see that we need a complement of this value that we have read from here to be put onto port 0 for getting the corresponding pattern. So, this is done here. So, after getting that P1 port content into accumulator A, so we are complementing A, and this complementing A will complement the bits. So, all the bits are complemented, and then move P0 comma A. So, move P0 comma A. So, this will output the data to P0 for the LEDs. So, this will be outputting this P0 A. So, this will be this pattern will go to P0, and then SJMP main. So, we again go here. So, you can again I have to make this read line high. Okay, another. So, by this time I am ready to sample the next data from the ADC. So, that I should give another read signal, another write signal to the ADC. So, that is given here by a high to low pulse on the read line, on the write line, low to high pulse on the write line, and then again it will do the conversion. So, this process goes on. So, in some cases, so we have got an this INTR signal in some of the processors. You will find that this INTR line, so it is also known as end of conversion. So, this pin in many cases you will find it written as EOC or end of conversion, and this is the end of conversion pin, and then this right line, this I have already said that this is the start conversion. So, this type of conventions are there. So, if you are looking onto a different ADC, so you may find that these pins names are slightly different. So, this way you can connect ADCs with that. So, this particular ADC, this is a single channel ADC. So, there is only one channel on which you are feeding this V input, and it is converting that. So, in some of the ADCs, like there is the next ADC that we have is 0808 ADC. So, it will have more number of analog channels. Okay. So, that chip, so instead of having a single analog channel, so it can have a number of analog channels. So, there may be say 4 such analog channels, they are named as AN1 to AN4, and then there will be corresponding some select lines will be also be required from the microcontroller. So, you can tell which analog channel you are going to convert by setting these select lines, and accordingly the conversion will be done, and the converted value will be available on the data bus. So, that way we have got multi-channel ADCs also. So, these are commonly known as multi-channel ADCs. So, they are useful for if we have got several analog quantities to be converted into digital value. So, they can be useful for that.